Okay, this lecture is analysis of variance part 2. So this is a continuation from the first lecture where I introduced analysis to variance. So recall that analysis of variance is a hypothesis testing procedure for comparing means of two or more groups. We do an analysis of variance because doing multiple t-tests increases the probability of making a type 1 error. Recall that a type 1 error is saying that there is a true effect in the population when indeed there isn't. So we say that we have a statistically significant result when we don't. By convention, we set our chance of making a type 1 error at an alpha level of 0.05 in psychology and other social behavioral sciences. But what happens is that for a single test, if we have alpha set at 0.05, when we do multiple tests with that alpha set at 0.05, that error can accumulate over every test that we do. So rather than doing multiple tests, multiple t-tests comparing different say pairs of means, we start by doing a single analysis of variance. And in that single analysis of variance, we can set alpha at 0.05, and in doing so, we maintain the probability of making a type 1 error at 0.05. So what our analysis of variance tests is whether the means of our samples differ more than expected by chance alone if the null hypothesis is true. And what we calculate with an ANOVA is an F ratio. That F ratio is the between groups estimate of population variance over or divided by the within groups estimate of population variance. As I introduced in the previous lecture, essentially what we're doing with the F ratio is we're coming up with two different methods of essentially estimating the same thing, which is the population variance. So here's the logic. If the null hypothesis is true, then population variance that is estimated from variance between means should be the same as the variance estimated from within each sample. So we can kind of imagine that we've got three different groups of people. In the previous example, we talked about people that had different attachment styles. They could be securely attached, avoidantly attached, or anxiously attached. If the null hypothesis is true, those populations are identical. Same mean, same variance, same shape. So I've just put the three population distributions here so you could see them, but really under the null hypothesis, these three population distributions would be exactly overlapped or overlaid on one another. So it would look like there's just one there, but I wanted to show you that there's three. So under the null hypothesis, regardless of whether we estimate the population variance using the variance from each of our samples, kind of that pooled estimate of variance, the within approach, or whether we estimate the population variance using the between means approach, we should converge on the same thing. We should get the same number under the null hypothesis within a certain amount of error. However, if the null hypothesis is not true, the population variance that is estimated from the variance between sample means should be more than the variance estimated from within each sample. And that's what this looks like at a population level. So what you'll notice is that the variance that we would estimate within each sample will be the same if in this example here. So if the null hypothesis is not true or whether the null hypothesis is true, the variance of the populations is the same. And so if we just take random samples from within each of these populations, calculate the variance within each of those samples, and then pool those together, that'll give us the same estimate using this within technique if the null hypothesis is true or if it isn't. However, if we estimate the population variance using the between means approach, if the populations are all overlapped exactly on one another, we sample a mean, sample a mean, sample a mean, there should be less variability between those sample means than there would be when the null hypothesis is not true, and there is some true effect in the population. For example, if securely attached people report more trust than people that are anxiously attached or avoidantly attached. So if there is a true effect in the population, there's a true treatment effect. One population is different than the other two as just one way that there could be some sort of an effect, then we should see a difference when we between those means. And then when we estimate the population variance based on that between mean approach, we'll get a higher or a larger estimate of population variance than we get from the within. All right, so let's just do another example. So I went over an example in the last lecture, but let's just do another one to try to get a feel for how we calculate these F ratios. So we're just going to do another, I guess I had relationships on the mind as I was creating these examples, but we're just going to ask whether being in a relationship affects how happy one is in life. And in our example, a statistics instructor asked his students whether they had a significant other. Okay, so that could be a boyfriend, a girlfriend, or a spouse. But there was 3 choices. So people could say, yes, I have a significant other. No, I don't. Or third category, it's complicated. And I'm sure at some point in our lives, we've been in that situation where you couldn't quite say yes, you couldn't quite say no. You were in a complicated situation with your significant other. All right. And then students also indicated their agreement to the statement, I am happy in life, on a 5-point scale where 0 was not at all and 4 was extremely. So basically higher numbers mean more happiness. And here's what we have. So we've got 10 people in each group. We've got the average level of happiness in each sample. And then the other thing that we have is an estimate of population variance that has been calculated from the sample variance. Okay, so again, let's just keep in mind, what I'm not reporting here is a variance or a standard deviation as a descriptive statistic. I've gone ahead and done the sum of squared deviations from the mean divided by degrees of freedom, which is 9, and that gives me an estimate of population variance. What you'll see is that there's a different estimate of population variance from each of these 3 groups. Why would that be the case? Because among each of the groups of 10 people, there's a different amount of variability in each of these samples. That is, the 10 people in the yes group, there's a different amount of variability from their sample mean. Among the 10 people in the no group, there's a different amount of variability from their sample mean. And among the 10 people in the it's complicated, we can see based on the population estimate, there's more variability around that mean. Okay, so in those samples, there's different variability, and we're going to use that to say, well, under the null hypothesis, all of these groups are supposed to be identical in terms of their population mean and in terms of their population variance. We know whenever we take a sample from a population, our sample statistics will be in error to some degree, and so we're just going to use a averaging procedure to say, each one of these numbers should be telling me what the population variance is. Each one of them is likely to be in error to some degree. So as a way to get the best, most reliable estimate of what the true population variance is, I will just average them together. Okay. So I'm skipping ahead a little bit, but let's start with our research question. Are there differences in happiness between people who have different relationship statuses? As in, we can kind of eyeball these means, but can we say that these means are statistically different from one another? We're going to restate the question as a research hypothesis and a null hypothesis about populations. Population 1 said yes, they have a significant other. Population 2, no, they don't. And 3, it's complicated. This is just arbitrary. We could call whichever group we wanted population 1, 2, or 3, but the idea is that we're talking about populations of people. We took samples of 10, but we're ultimately making hypotheses about the entire population of people. Under the null hypothesis, we'll say that mu1 is equal to mu2 is equal to mu3. So under the null hypothesis, all of these 3 populations of people would be equally happy. Okay, under the null hypothesis, relationship status doesn't matter. Alternatively, under the research hypothesis, otherwise known as the alternative hypothesis, we simply say that the population's means are not the same. So the hypotheses are relatively simple and straightforward in analysis of variance. The null hypothesis will always be mu1 equal to mu2 equal to mu3 equal to mu4 equal to mu5, depending on how many groups that we have. Basically, all means equal. Not the m's, not the sample means, but the mu's, those squiggly u-looking things. And then the alternative hypothesis is simply the population means are not the same. Second, we're going to determine the characteristics of the comparison distribution. This will be an F distribution. It looks like this. It has a mode of 1. It is positively skewed. We determine the degrees of freedom for our comparison distribution by taking the degrees of freedom figured between groups, which we take the number of groups minus 1. So we have 3 groups in this example. Minus 1 is 2 degrees of freedom between. We have 27 total degrees of freedom within. We do that by adding the degrees of freedom within each of our groups. So we had 10 people in each group. 10 minus 1 is 9. 9 plus 9 plus 9 is 27. So we will have a unique F distribution depending on our research question and our research design. Okay, so there's many different F distributions. And the exact shape of that F distribution, which is a sampling distribution, okay, it is determined by degrees of freedom between and degrees of freedom within. So again, there's not a single F distribution. You can think of having a family of F distributions. The next thing we're going to do is determine the critical value on the comparison distribution at which the null hypothesis should be rejected. The critical value for an F critical with 2 degrees of freedom between and 27 within, setting our alpha level at 0.05, is 3.36. I don't think I show the table in this lecture, so just take my word for it. But if you don't want to take my word for it, you can use table A3 in our textbook and find that the critical value should be 3.36. Next thing we're going to do is determine our sample score on the comparison distribution. So what we ultimately want to get to is an F ratio. The way we get to our F ratio is we're going to calculate S squared, that is our estimate of population variance, based on the within groups approach as well as the between groups approach. Let's start with the within groups approach. We do that by simply pooling together each of our estimates of population variance from each of our 3 groups. So this is nothing more than a simple averaging of each of those estimates of population variance. So in this case, what I'm doing is just averaging 0.50, 0.54, and 1.03 by adding them together and dividing by 3. So our estimate of population variance figured using this within groups approach is 0.7. And the reason that we can do this and we don't have to do a more complicated weighted procedure based on different degrees of freedom is because we have the same sample size. So we're weighting each one of these estimates the same. Okay? So we can only use this formula when we have an equal n in each group. For the purposes of this class, we're only going to be using examples in which n is equal in each of our groups. Okay, the next thing that we're going to do is figure out our estimate of population variance using the between groups approach. This is a 2-step procedure. So part B is a 2-step procedure. The first part of the procedure is to estimate the variance of the distribution of means using the sum of squares from our sample means. So basically what we're doing here is we're treating each one of our means as a little mini sampling distribution. We could keep repeatedly sampling from our population. We've got 3 samples here, but we could take a 4th, we could take a 5th, we could take a 6th, we could take a 7th. And so what we're kind of imagining is that we're forming a distribution of means. Recall that there is a relationship, there's a very close relationship between the variance of the distribution of means and the variance in the population. The more variance there is among in the distribution of means, the more variance there is in the population. The less variance there is in the distribution of means, the less there is in the population. So the short of it is the variance of the distribution of means can tell us what the variance in the population is. So this is kind of a working backwards procedure. Previously with our t-tests, we've been estimating the population variance and then using that population variance to tell us about the variance in our distribution of means. Here, we're just going to reverse the process and figure out what is the variance in our distribution of means and then use that to work backwards and get the population variance. Okay, so the first thing, we're just going to calculate our variance of the distribution of means, and we do this by getting our sum of squares. So the first thing that we need is our grand mean. So to get our grand mean, we just average 3.5, 3.1, and 2.8. That gives us an average of those three means of 3.13. Then what we're going to do is figure out what is the squared deviation of each of our means from that grand mean, and then we're ultimately going to divide that by degrees of freedom. So this is nothing more than calculating a variance, really an estimated variance, and we're using degrees of freedom because we're estimating what the variance of the distribution of means is, basically using a mini sample of 3. We don't have all the means in the distribution of means. So we're just going to use degrees of freedom to reflect that this is an estimate. Okay, so again, what we're figuring out is we're not yet figuring out the population variance, we're figuring out the variance of the distribution of means. And so doing that, we're just plugging in 3.13 for our grand mean, again, taking the deviation of each of our sample means, squaring that deviation, and then dividing by degrees of freedom, which is in this case is 2. So that gives us a variance of our distribution of means of 0.123. And then what we're going to do is use that to estimate the population variance. And this is just kind of our working backwards procedure. Previously, what we did to get the variance of the distribution of means is divide the population variance by n. So just by a little bit of algebra, we're just going to move that n over to the other side. And so by multiplying our variance of the distribution of means by sample size 10, that will give us, that's another way to estimate what our population variance is. Okay, so doing that, we're going to multiply 0.123 by 10, which is our sample size, and that gives us an estimate of population variance, which is 1.23. Last step, we need to figure out the F ratio. That's done by dividing our S squared between by S squared within. So we just calculated S squared between of 1.23. We had previously calculated our S squared within of 0.7. That yields an F ratio of 1.76. And when we need to just compare that to our F critical of 3.36, and we need to say, does the F that we calculated of 1.76, does that exceed our critical value of 3.36? Does it land in the critical region or does it not? And of course we can see that it does not fall in the critical region. Therefore, we are going to fail to reject the null hypothesis. What does it mean? There is insufficient evidence to conclude that the differences observed between the groups are greater than the differences expected by chance if all samples were drawn from populations with identical means. Okay, so yes, those means are different. Let me just run back and take a look at these means. These means are different. Certainly they are. Okay, but they are not so different to preclude the possibility that they could not have been sampled from populations with identical means. Okay, so these sample means, it's possible we could have gotten sample means that were this different even if they were all sampled from populations with the exact same mu. So what we're saying is we don't have enough evidence to reject the null hypothesis. And so at this moment, we are going to fail to reject the null hypothesis. We'll retain the null, and we have to accept mu1 equal to mu2 equal to mu3. And therefore, our data do not support the idea that a person's relationship status affects his or her current happiness. And you can think for yourselves whether you believe that that is true or not, but the data that we had did not support that idea. All right. Now, what I want to do is return to the previous example that we had in the last lecture And this was looking at the amount of trust that people report in their current relationships if they have a secure, avoidant, or anxious, ambivalent attachment style. We had previously calculated an F of 5.15, which was a statistically significant result. And so we were able to say that people with different attachment styles differ in the amount of trust that they feel towards their romantic partners. And this is what a write-up would look like if you would read this in a scientific journal. You'd have a statement that looked like this. You'd have an F that equals 5.15, just what we calculated. One thing that you do in reporting results is share the degrees of freedom, because this gives the reader of your research report a sense of how many groups were in the study. Okay, so people that know statistics know that this first number reflects degrees of freedom between. That means that there's 3 groups. Degrees of freedom within, this reflects, this gives the reader a sense of what your sample size is in each group. So by convention, you report those degrees of freedom, and then you indicate whether that result was statistically significant by saying that the probability of getting this F is either less than 0.05 or more than 0.05. Okay, so what that communicates is our sample result happens less than 5% of the time, assuming that the null is true. Therefore, we reject the null. The population means are not the same. But what this does not tell us, okay, think about what we've rejected. The null hypothesis was mu1 equals mu2 equals mu3. We've rejected that, but we haven't been able to make any conclusions yet about which mean is different from which other mean. Okay, so that's our question. Which means are different from one another? So what we have to do is when we have a significant ANOVA, we have to follow it up. The ANOVA itself is known as an omnibus test, which means overall. It can tell us whether there's an overall difference among several groups or several means. Okay, it tests the omnibus null hypothesis that all the means are equal. So when we reject that null, we are rejecting the null hypothesis that all the means are equal, but we can't say anything other than that. When we do research, we're typically interested in specific differences between groups. So what we want to do is a follow-up, and we can test specific differences. Now we can do that ahead of time. So before a researcher even goes out and collects the data, they might have planned contrasts, otherwise known as a priori comparisons, okay, ahead of time comparisons that they have in their mind that they want to do. And so before they even collect the data, they might say to themselves, I would really like to know, do people that are securely attached, do they have a different amount of trust in their relationships than people who are avoidantly attached? And do people who are securely attached have a different amount of trust than people who are anxious and ambivalent? So like those two comparisons might be planned in advance. Alternatively, comparisons could be unplanned. Okay, these are known as post hoc comparisons. In other words, after the fact. That's what post hoc means, after the fact comparisons. So it could be the case that there's no prediction or hypothesis as to whether avoidantly attached and anxious ambivalent attached individuals differ in their degree of trust. But after collecting the data, a researcher might say, but let me test it out. Let me figure that out. So if there's no planned hypothesis in advance, but we just want to explore the data, that's an unplanned or a post hoc comparison. And those two things are treated differently in statistical testing, which I'll elaborate on in just a little bit. Another way to think about testing differences between groups is that we can think of testing differences as either being simple, which would just be a planned comparison between only two groups. And I should say that you could have a post hoc comparison there. So we can say planned or post hoc comparison between only two groups. But a simple comparison is a comparison between only two groups. In contrast, we have what are known as complex comparisons, which we compare multiple means. So for example, you could take one group versus the average of all the other groups. So a researcher might want to know, are securely attached people more trusting? Do they report more trust in their relationship than the other two groups, right? So what you do there is you just lump together anxious people and avoidant people. You'd lump them in as one category, calculate their average, and test whether securely attached people are different than that entire group of folks. Okay, that's an example of a complex comparison. If we had a 4-group design, you could test the average of 2 groups versus 2 other groups. Okay, so those are complex comparisons. So anytime we're testing more than just 2 means, we've got a complex comparison. You will be happy to know that in this class, we're only going to learn how to perform a simple comparison and then how to adjust our procedure depending on whether that simple comparison is either planned ahead of time, a priori, or unplanned post hoc. In an advanced statistics class, you'll learn how to do complex comparisons, but don't worry about it for the purposes of this class. We're just going to be worried about simple comparisons or simple contrasts. So, how do we do that? Okay, so again, recall that a planned, and I use contrast and comparison interchangeably, they're the same. A planned contrast, which is a simple comparison, which only compares 2 means, can be conducted using the following procedure. We're going to use the within groups population variance estimate that we've already calculated from our omnibus analysis. So that step is done. We're going to calculate a new between group variance estimate using only our 2 means of interest. Then we're going to figure the F ratio in the usual way. So there's only a slight modification to the procedure that we've already learned. And then we have to come up with a new critical value for F because our degrees of freedom have changed in the numerator. Okay, so our numerator, because we're only comparing means from 2 groups, our degrees of freedom will always be 1. 2 groups, n equals 2, so n minus 1 is 1. So degrees of freedom in the numerator for a follow-up simple comparison will always be 1, and then we're just going to keep the same degrees of freedom in the denominator. So whatever the degrees of freedom are for the within groups estimate, that's going to stay the same. So it's really just a slight modification on what you've already done. All right, so let's just say we wanted to do this simple contrast ahead of time before the researcher even collected their data. They had the hypothesis, or they wanted to answer the question, do people with a secure attachment style trust their partners more than people with an avoidant attachment style? That is comparing secure to avoidant. And let's just say the researcher had the prediction that securely attached people report more trust or have more trust in their relationship than avoidant. Okay, so the mean for secure is greater than the mean for avoidant, and then the null hypothesis is that that mean would be less than or equal to the mean from avoidant. So, okay, animation. So we're just going to use the same within groups estimate of variance. Recall we already calculated this. So that was our formula, that was our procedure, and this step, it's already done. So when doing a simple plan comparison, the first step is already done. We're just going to use our within groups estimate of variance. The second step, though, we have to do, where we have to estimate the population variance from the differences between only the 2 group means of interest. So we're going to use this between groups approach, but we just got to redo this formula and this calculation based on only the 2 group means of interest. So there's, again, the step 1 of that and then the step 2. Okay, so here's our 2 means of interest. What do we need to do? The first thing we have to do is estimate the variance of the distribution of means. There we go. And so that involves calculating our grand mean. Again, you can see only among the 2 means of interest. So the average of 4.2 and 3 is 3.6. We're then going to use the exact same formula. Degrees of freedom, again, will always be 1 when doing a simple comparison because there's only 2 groups. So it's a very simplified version of this calculation. So in calculating the variance of the distribution of means here, we get that that's equal to 0.72. Second step, we're just going to multiply that 0.72 by 5, which is n, to get our estimate of the population variance. That's 3.6. Calculate our F ratio in the same way. So we take 3.6 divided by 0.67, which was our within estimate. That yields an F of 5.37. Okay. We of course need to evaluate that relative to a critical F. So we need to determine the critical value. So again, degrees of freedom will be 1. We're going to use the same degrees of freedom within, which is 12. Okay, to understand why that's 12, recall that we had 5 people in each group. So degrees of freedom in each group is 4. We had 3 groups, so 4 plus 4 plus 4 is 12. So looking up our critical value, this is an abbreviated table. I've obviously cut out the lines. Our numerator degrees of freedom is 1. Our denominator degrees of freedom, that is the bottom of the ratio, is 12. Alpha 0.05. That gives us a critical value of 4.75. Okay, so there's our F critical. So we are just going to compare the F ratio that we calculated to that F critical. We see that our F ratio of 5.37 is greater than the critical value. So do we reject the null? Yes, we do. And we can say, well, let's take a look at what that null was. The null hypothesis was that the mean for securely attached folks will be less than the mean for the avoidantly attached folks. We have an F that is greater than the critical ratio, but we of course do want to make sure that our sample means were in the appropriate direction. And so yes, we're going to reject the null. We got an F that is larger than the critical, and what we see from our descriptive statistics is that the means were in the correct direction. So we have a directional hypothesis, so we have to make sure that the means are in the expected direction. And this should be that should be a 4.2, not a 4, but all right. So it's important to look at the means to make sure that they're in the predicted direction. All right, so that's if we had planned that to test that hypothesis ahead of time before we collected our data. Sometimes researchers do analyses and they do an analysis of variance comparing the means for several groups, but they don't necessarily have predictions ahead of time which means will be different from which other means. And so they need to use a set of procedures that will allow them to test for those differences, but also not kind of falling into the trap that ANOVA is meant to avoid in the first place, which is accumulating experiment-wise error. That is, we don't want to do multiple tests all at an alpha of 0.05 and then keep accumulating the probability of making a type 1 error by doing all of these multiple comparisons. So that's why statisticians have developed procedures for doing after the fact or post hoc comparisons. So in the event we don't have specific hypotheses ahead of time, we're going to do post hoc comparisons, and ultimately we're going to compare specific means that were not decided in advance before we looked at our data. They're often conducted as part of exploratory analyses or to thoroughly explain a set of findings. So you might say, why would you be testing differences between groups if you didn't have hypotheses or predictions about it? Like, it would seem that you wouldn't care. Sometimes it's just done to fully explore the research data. So a variety of procedures have been developed. In fact, when you use a statistical software program, there are as many as 20 different procedures for doing post hoc analyses and comparisons. We are not going to learn 20, we're only going to learn 2. But generally what you should know is that post hoc comparisons, including the 2 that you're going to learn here in this lecture and all the others that you could possibly use in a statistical software program, they've all been designed to keep the risk of making a type 1 error at some level, like alpha 0.05, while at the same time not reducing statistical power too drastically. Recall that when we lower the alpha level to something like 0.01, we've made our test more stringent. And so it becomes more difficult to make a type 1 error but it also uh, it becomes more difficult to have it becomes more difficult to have a statistically significant result. So we make it more difficult to find statistical significance. So it's easier to make a type 2 error in that event. So we want to strike a balance between keeping our alpha somewhere around 0.05 in total and having as much statistical power as possible. So that's what these procedures are developed to do. So we're going to learn the Bonferroni correction as well as the Tukey test. These are two very popular and widely used post hoc comparisons. And by the way, I'm talking about post hoc. Some people would advocate, even when you do many planned comparisons, you should even use some of these corrections as well. So that is, if you're going to do a lot of comparisons, there are some people that would advocate for making these types of corrections to guard against a type 1 error. All right, so all a Bonferroni correction is nothing more than a corrected alpha level. And all that's done is you take whatever alpha level is conventional, and again, it's usually 0.05 in psychology and social sciences, and then you divide that by the number of tests or comparisons that you're going to do. So if you're going to do 2 comparisons, alpha would be set at 0.05. That is, when you determine your critical value for F, instead of using alpha 0.05, you're going to use alpha of 0.025. So if we wanted to test whether securely attached folks are different from avoidant and whether securely attached folks are different from anxious, that's 2 comparisons. If we're doing a Bonferroni correction, we're going to divide our alpha 0.05 by 2, and we're going to set our alpha at 0.05. If we've got a very large research design and we're going to do as many as 10 different planned comparisons, alpha, that is your significance level for each one of those tests, would be set at 0.005. That's just 0.05 divided by 10. Okay? So essentially what you do is for any single test, you make it more difficult to achieve statistical significance on any single test. And that's a trade-off because what you ultimately want to do is be confident that you're not making a type 1 error. Now, it turns out that when you do, and in the real world, most analyses are done using statistical software. And when you do that, the statistical software will give you the exact significance probabilities as a part of the output. So that is, you might calculate an F, and your statistical software will say that the probability of getting this F is 0.037, or the probability of getting this F is 0.054. Not just whether you've surpassed the critical level at either the 0.05 or 0.01 level. Okay, so in other words, using a statistical software, it doesn't have the step of having to look up a critical value in a table. That's what a statistical software allows us to do. So what we can do is just say, okay, well, I set my Bonferroni correction at 0.025. Did my P level surpass that? Okay, is it below? In this case, if I had set my Bonferroni correction at alpha 0.025, well, I didn't make it because I needed to be significant at less than 0.025, and I'm not. I was less than 0.05, but I'm not less than the 0.025 that I set with my Bonferroni correction. If I got a result like this, hey, that's good. If I had set my Bonferroni correction at 0.025, I made it. That's a probability that is less than that 0.025. So the thing with tables is it's kind of an antiquated thing. We use these statistical tables when we're teaching statistics, but very rarely do researchers rely on tables. They're using statistical software. That being said, there's some traditions that are still followed today. So if you take an alpha of 0.05 and then you divide it, you might get a Bonferroni cutoff that is 0.017 or even 0.025. Some researchers will just say, well, if I was to use a table, I would have a choice between the 0.05 cutoff or the 0.01. I know the whole point of this is to do something more stringent than the 0.05. I'll just default to 0.01, in which case they would look up the critical value associated with 0.01, even though the Bonferroni correction would suggest to only use 0.017 or 0.025. Also, by convention, if there's only a small number of planned contrasts, or even 3, it is common for researchers not to correct at all. So again, if it's a post hoc and after the fact, you should absolutely correct. If you're doing multiple planned comparisons, if you're only doing a small number of these planned comparisons, most people say we don't need to correct at all, because after all, they're planned. If they're after the fact post hoc, yes, correct, but it's generally accepted that if we're doing planned contrasts, even if we're doing multiple, like 2 or 3, we won't correct. It's only when we start doing 4 or 5 or 6 that it is considered best practice to do a Bonferroni correction. All right, here's the second one, the Tukey's HSD test. This is a nice statistic because it allows you to compute a single value that determines the minimum difference between group means that's necessary for statistical significance. So this very quickly and efficiently will allow us to basically make all pairwise comparisons. So the value that we'll come up with is something that's called the honestly significant difference, or HSD. If the differences between the means in our groups exceed this honestly significant difference, the difference is statistically significant. Here's the formula. You'll notice that 2 elements in the formula are very familiar already. We've got the mean squared within. Okay, this is, again, same thing as the S squared within. This is our estimate of population variance figured out using the within group method. And in our example, we've already calculated this. You'll see we have N, which is the sample size, okay, for each group. And then the only thing that's new is this Q. The value of Q can be found in a lookup table. It's the value of this Q is based on the number of groups, degrees of freedom, and the desired alpha level. So very similar to how we're used to looking up critical values of things. Okay, so the mean square within comes from the ANOVA. We've already calculated it. N is the number of people in each group. To calculate this statistic by hand, the group size must be equal. So in our current example, Q is 3.77. I've got a hyperlink here to a table. If you want to look that up for yourself, go ahead and do it. Otherwise, you can just take my word for it. On an exam, this Q value will be given to you. Okay, our mean square within from our example was 0.67, N was 5. So really it's just a matter of plugging in numbers. Okay, so we've got 3.77 multiplied by the square root of 0.67 divided by 5. That gives us an honestly significant difference of 1.38. So the way that we're going to use this honestly significant difference is to say, among our 3 sample means, securely attached, avoidantly attached, anxious ambivalent, is the difference between those means greater than 1.38? And if it is, we'll have a statistically significant result. Okay. So here we go. Our differences between our means need to be greater than 1.38 to be significant. Well, let's take a look at this first comparison, secure versus avoidant. 4.12 and 3. That's a difference of 1.2. That difference of 1.2 is not greater than 1.38. Therefore, using the Tukey's HSD procedure, we would not say that secure and avoidant are different than one another. Okay? This is not a statistically significant difference based on Tukey's HSD. What about our second comparison? Secure versus anxious ambivalent. The difference between 4.2 and 2.6 is, let me do the math, 1.6. So we've got a difference of 1.6 between secure and anxious ambivalent. That difference of 1.6 does exceed the honestly significant difference. So we would conclude that there is a statistically significant difference in the amount of trust that securely attached versus anxious ambivalent attached folks report. And then we can clearly see that the difference of 0.4 here isn't big enough to be bigger than that HSD. Okay, so using Tukey's HSD, we would conclude that the secure group reports more trust on average than the anxious ambivalent, darn it, but not avoidant. Notice that the first decision that we made during this analysis, which is that secure, not different than avoidant, is different than our decision when we did the planned comparison. When we did the planned comparison, we found that there was a statistically significant difference between secure and avoidant. So why the difference here? Why are we coming up with a different statistical decision? When we did the planned contrast, we got a statistically significant result and we said, hey, those groups are different. Population level, those groups are different. Here we're saying, no, they're not. This is due to the more stringent nature of the post hoc test. Post hoc tests make it more difficult to find statistical significance because they're guarding against making a type 1 error. So we need to see a bigger difference among means in our sample data in order to conclude that they're statistically significant when we do a post hoc comparison. When we do a planned comparison, because we made the prediction ahead of time, there's already a certain level of confidence that those means ought to be different, and that's based on prior theory or some good reason. We give ourselves a little bit more latitude in that we can use that alpha 0.05. Here we're using a corrected, kind of behind the scenes, we're using a corrected alpha level here. So it's possible, depending on whether you use a planned comparison versus a post hoc comparison, that you'll get a different statistical decision. Wow. All right. Let's talk about effect size for analysis of variance. Effect size is the proportion of variance accounted for, which is R squared. This is calculated using a somewhat complex or complicated equation, which I don't expect you to know or memorize or remember, as much as just interpret. My animations are all messed up. As much as just interpret what an R square means. So an R square, when we plug in our numbers, and you'll see that these are merely the numbers that we've been working with from our example calculation, an R squared reflects the proportion of variation in our outcome measure, trust, that can be accounted for or explained by group membership. All right, so let's think about this. We've got 3 different groups of people: secure, anxious, and avoidant. And all of those people report a different amount of trust. Now, there's other things that might cause people to report different levels of trust in their relationship. Attachment style is just one of those things. But I mean, there's like how long you've been together, and there's who you're with, and there's all kinds of things. So in other words, there's many reasons why we see variability in the amount of trust that people report in their relationships. But how much of that variability can attachment style explain? What this statistic tells us is 46% of the differences or the variability in why people have these different trust scores can be explained by or can be accounted by knowing their attachment style. Okay? So that's what that effect size tells us. Sorry, you're just going to have to bear with me. Darn. There we go. So R squared is also known as eta squared in the language of analysis of variance. So eta is this Greek symbol that kind of looks like an N. And there's conventions that have been developed for what's small, what's medium, what's large. So interestingly enough, an R squared or an eta squared of 0.01, that is explaining only 1% of the variability in an outcome, is considered a small effect, 6% is a medium effect, and 14% is a large effect. So in our example, we have a very, very large effect because attachment style accounts for 46% of the variance in trust ratings. Why do these numbers seem so low? Well, these are conventions primarily in social and behavioral sciences, and I think a lot of it has to do with people's behavior is variable, and the measurement that we have for measuring attitudes and behaviors is imperfect. So being able to explain a small percentage of attitudes, feelings, cognitions, behaviors, etc. is, 14% is considered impressive. All right. So let's just end with talking about some of the assumptions of analysis of variance. I've been speaking to them this whole time, but let's just make it explicit. The first assumption is that, and really the main assumption is that all populations are normally distributed. If it is the case that in reality we would have some reason to know that populations would not be normally distributed, this isn't going to mess up conducting an analysis of variance. And so statisticians have determined that so long as you have a big sample size, then doing an analysis of variance is robust to moderate violations. There can be problems if the populations are skewed in very different directions. So if you think about, securely attached people, most people report a lot of trust, but then you have that tail on the left-hand side where there's a small number of people that don't report much at all, and then like avoidant people would be just the opposite. So if there's some reason to believe that at the population level the distributions are skewed a lot and they're skewed in opposite directions, that would be a problem for running an ANOVA, but under most circumstances it's not a problem. And then the second assumption is that all populations have the same variance. This too is robust to moderate violations. It would be a problem when the largest variance estimate of any group is 4 or 5 times that of the smallest. Okay, so I think in some of our examples we've had, clearly the variance has been different, but it's only a problem if you look at the smallest variance estimate, the largest variance estimate, and that largest variance estimate is 4 to 5 times that of the smallest. Okay, otherwise not a problem.